So this lecture is all about inhibition. Mostly we've talked about excitatory associations. Show a key light to a bird in auto shaping, follow that with food, do it several times. The key light is represented in the brain, makes an association, excitatory association, with an area of the brain that is involved with food or in pecking, right? SS, SR associations. Inhibition, on the other hand, is also learning, according to Pavlov, but this is learning that the reinforcement is not coming. If the CS is presented, then they know that what follows is nothing. This is especially important, according to Pavlov, in excitatory context. In other words, there was some expectation. Ring a bell, give a dog food over and over. You ring the bell, the dog's thinking, okay, I'm about to get some food. There's some association. I didn't get any food. That's learning. That bell signals nothing. When I expected to get something, I expected to get food. Internal inhibition, this is a representation of inhibition in the brain, signals non-reinforcement when in an excitatory context. What that means is simply there's some expectation that something's going to follow, a shock or food or whatever, and it doesn't happen. That is non-reinforcement when reinforcement is expected. So there are many types of experiments that create inhibition in research. We've talked about one. This is extinction. So stimulus A is followed by reinforcement for many trials. Maybe we reach asymptote. Maybe we reach a high level of conditioned response. Then the same CS is presented without the US for many trials, and we see the conditioned response go down. Talked a little bit about this, the fact that Pavlov thought during extinction, inhibitory associations are created. Inhibitory associations compete with excitatory associations, so performance goes down. The evidence that inhibition is created came from spontaneous recovery, disinhibition, and rapid reacquisition. But at the beginning of extinction, the animal expects that the CS, stimulus A, is going to be followed with reinforcement because it's been that way for a long time and now it's not, so inhibition is created. This is something we're going to talk about in this lecture. This is known as conditioned inhibition. Conditioned inhibition. And the procedure for this is one stimulus is followed by reinforcement, but not when in combination with another stimulus and go back and forth. B plus, BA minus. Could be just as simply A plus, AB minus. What that means is, let's give an example. Ring a bell, give the dog food, ring a bell and play a tone, and the animal gets nothing. Bell food, bell tone, nothing. Bell food, bell tone, nothing. Now the reason that B gains inhibition is because A is signaling to the animal, I'm about to get some food. I'm about to get a reinforcement. But now I'm not. What is telling me that? What learning is taking place? That other stimulus, that tone, tells me I'm not getting reinforced. What is the excitatory context? Stimulus A. Finally, we have what's called differential conditioning. And in this case, one stimulus is reinforced and the other is not. Now this creates sort of a larger context of reinforcement. The animal's in a cage, it's getting reinforced, or it's in a lab. And a bell is presented and it gets food. A is presented and it's not getting food. Back and forth, back and forth. Now that creates some expectations. I get some food here. Or if we're talking auto shaping, the bird is sitting there and sometimes a blue light is presented and I get food, but a yellow light's not. But still I get food here. I'm in a context where I should be getting some food. So A gains inhibition and B gains excitation. And finally, we have a procedure called latent inhibition. And there's some controversy on this, on whether this produces internal inhibition, a signal of non-reinforcement. This is just presenting a stimulus over and over to an animal and not reinforcing it. Doesn't really have the excitatory context, but we'll see in a moment. Some people say, well, it seems to pass a test for inhibition, so maybe it's inhibitory. So, extinction, conditioned inhibition, differential conditioning, and latent inhibition. And latent inhibition is kind of a question mark. We'll talk about that. So let's look at conditioned inhibition. Real simple. One stimulus A, whatever, a yellow light, whatever, is presented with food, an unconditioned stimulus. We could do conditioned suppression just as easy. A light is followed by shock. We could do auto-shaping. A light is followed by birdseed. Right? There's lots of procedures. But when the stimulus that was reinforced is presented in compound with another stimulus, it's not reinforced, and we go back and forth. Food, yellow, red, no food. Yellow, food, yellow, red, no food. And we do this over and over. And what happens is red gains inhibition because it's a signal of non-reinforcement, a signal that the US is not coming when the US is expected. Why is it expected? Well, the yellow light. The yellow light has been associated or presented in temporal contiguity with a US, but not when it's presented with this other stimulus. This stimulus is a signal of non-reinforcement. So which of those stimuli signals non-reinforcement? The red. What is the excitatory context? The yellow light, that stimulus that signals food. How do we know the red light signals non-reinforcement? Because we have a situation where the yellow light, if we're talking about a Pavlovian experiment, that's going to produce salivation. But the red light produces nothing. The animal doesn't respond at all to the red light, but you know what? It would not respond to a bell, and it would not respond to a bunch of other stimuli that aren't associated with food. The animal doesn't respond to red, but it doesn't respond to many other things. So how do we test? So let's look at some tests of inhibition. There are 3 basic tests to determine if a stimulus has internal inhibition. One is called a direct behavior test, which I'm not going to really talk about. A direct behavior test might be something like in an auto shaping. A key light comes on and a bird pecks it, and the key light is a red light, or a yellow light. Let's keep the same stimuli. Yellow light, bird seed, yellow red light, no bird seed. When the red light comes on, the pigeons just tend to walk away from it. We call that a direct behavior test. It's just not, it walks away from where it gets food. The 2 I would like to focus on, that I'd like you to know about, is called the retardation of acquisition test and the summation test. Know the procedures and know what we get. So let's look at a design. We have a design here. We have 2 groups of animals. We are, let's say, doing auto shaping with pigeons, and these are key light colors, just as an example. This is a retardation of acquisition test. I know the word retarded has come to be a slur or a negative word for somebody who has mental disabilities. But retardation, just as a word, just means slow. And this test was developed in, I think, the 1950s or 60s. And it just means slow to learn. That's all. So don't read into it too much. Here's how we'll do it. Group 1 gets 2 sets of stimuli. It gets a blue, followed with food, and then blue with yellow, followed with no food. Back and forth. Blue food, blue and yellow, no food. Blue food, blue and yellow, no food. And we do this over and over, and we measure its pecking behavior, its probability of pecking. We have a control group. The control group is very similar. Blue light food is a different group. Blue and orange, no food. Blue, food. Blue, orange, no food. Those are the stimuli, back and forth. Which of the colors would you say is excitatory? Right, it's the blue because it's been associated with food. Which of the colors is inhibitory? It's the yellow because it's not reinforced with food, but the orange is also inhibitory because it's not reinforced in the context of blue where it normally gets reinforced. Then you take both groups and you train them that yellow is associated with food. Wait, I thought you said yellow was inhibitory. It is. If the yellow signals no food, one would think that now, to try to convince the animal that yellow does signal food, well, that's kind of a counter conditioning. That would take a while. But yellow really doesn't mean anything for group 2. Yellow starts relatively neutral. And so it should reach an asymptotic level of performance faster than the other group where yellow is a signal of non-reinforcement. In other words, group 1 would be slow to learn compared to group 2. Group 1 is retarded in its acquisition of association compared to group 2. So we might just, this is just some measure of conditioned response, whatever that is. Don't worry too much about the y-axis. It could be a probability of pecking a key. It could be other things. And we just simply say, trial after trial, this is yellow associated with food. Yellow associated with food, each trial, yellow. This is after they've had this conditioning here. After this. And we see that in group 1, they aren't making that association, or they're at least not showing the conditioned response very well for a long time. So why are we getting this? It's because before, in group 1, yellow signaled no reinforcements coming. And now it's signaling it is. It's going to take the animal a long time to make that association and get up to an asymptotic level. What did yellow mean to group 2? It didn't mean anything. Animal's never seen it before during its training. And now it's associated with food and it's happy to learn very, very quickly. So, group 1 is slow to learn. We would say that it passes the retardation of acquisition test for inhibition. Yellow, when we then reinforce it, is slow to condition compared to yellow in this group. Yellow has never been seen in this group, so it learns very quickly. Yellow means something in this group. It means non-reinforcement, so it's slow to learn that now yellow does signal reinforcement. We say it passes the retardation of acquisition test. So now let's look at the summation test. First, we need to know what the summation rule is. The summation rule is relatively simple. It's the summing, the adding things together rule when it comes to association. The associative strength, I'm going to start using that term now, associative strength, strength of connection, strength of association of a compound stimulus, two stimuli shown together. In this case, it was yellow and blue or blue and orange. The associative strength of a compound stimulus is a summation, an adding of the associative strength of its compound. We're going to do something different from the auto shaping. We're just going to take a very simple example. We present a tone, beep, and we pair that with food for 5 trials with a dog, salivation. And we do that tone, food, 5 times. Not a lot. And then we say, well, what does the tone do? Beep. And we find that the animal salivates 2 drops of saliva. I'm making a very simple example. And then we take to the same dog, we present a light. Light comes on. It's paired with food for 5 trials until the dog salivates 2 drops of saliva. Right? When the light comes on, it salivates 2 drops. When the tone comes on, it salivates 2 drops. So what does the animal do when the tone and light are presented together? The association, the strength of that connection is summed. Now, this isn't exactly what happened, but I think you're going to get the idea. If we're showing the animal the light and playing the tone together in a compound, the animal salivates 4 drops of saliva. The behavior that we get from each is summed. Each has association. Bring them together, their association strength is added. So, tone plus food over and over, light plus food over and over. Test what happens when they're both presented together. Individually, the response is lower, but bring them together and the response sums because the association sums. That's called the summation rule, and it tends to work pretty well. So let's look at this experiment. An inhibitory stimulus, a stimulus that is inhibitory, it's a signal of non-reinforcement, will reduce the response to a known excitatory stimulus. This gets a little complicated. So what do we call this design here? B plus, BA minus, over and over. B plus, BA minus. Sometimes if we do things a lot back and forth, we'll put little arrows in there, or sometimes just a comma is how we use notation. B plus, BA minus. Now, what is excitatory and what is inhibitory? B is excitatory, A is inhibitory. Then we finish that. Then we take another stimulus, a new one, whole new, not A, not B, something new. So this might be a bell and a tone, and X counts as a light, whatever. And we condition X a whole bunch. We get it way up to an asymptotic level. We don't have to, but for this example, I think it helps. So the animal's responding a lot to this. Let's take auto shaping again. The probability of the animal pecking X is 95%. But then we take A and X and we put them together and we do a little test. We don't do this a lot. We just see, well, what does the animal do? If A signals non-reinforcement and X signals reinforcement, those two pieces of information should sum. And what should happen? The response should go down. Remember I said the animal responding 90% here? Well, now it responds 40%. Why? Because we have two pieces of information for the animal. X tells them that food is coming. A tells them it's absolutely not. I could get food any other time, but not when I see A because of this training. And it'll reduce. Now let's look at this one. This is our control group. So B plus, BC minus, B plus, BC minus, B plus, BC minus. Which is excitatory? B, because it's associated with a US, an unconditioned stimulus. A bell and food, a key light and bird seed, a tone and shock, a light and puff in the eye. Depends on the procedure. Either way, B tells them the reinforcement, the US is coming, but not when B is presented with C. So C becomes inhibitory. We finished that. A is inhibitory here, C is inhibitory here. We train X all the way up again, really strong, and then we present AX together. Now you might be saying, why aren't you adding C? Why isn't C and X together? Because this is a control group. We want to compare these two. What does the stimulus A mean to the animals in group 2? Is it excitatory? Signal of food? Signal of reinforcement? No. Is it inhibitory in this group? A is down. I'm definitely not going to get anything. I normally get stuff, but now no way. No. A has no meaning. A has no meaning either way. So what should it do to X in terms of its response? X tells them definitely food's coming and I'm going to respond to it 90% of the time. A means nothing. So I'm still going to respond 90% of the time. In this group, group 1, A signals non-reinforcement, but in group 2 it doesn't. So we would imagine response to one, in group 1 is much reduced compared to 2. That is the summation test. And if we get that, if we get group 1 responding to X much at a reduced level when A is present compared to group 2, we say, oh, A has passed the summation test for inhibition. This might be our response. This is just X by itself. No, there's no other stimulus, X. This is stimulus X and A, but in group 2. A doesn't mean anything in group 2, so they're about the same. It might reduce a little bit because we get this thing where, oh, there's something different that's distracting me, whatever. It means nothing, but it's a little distracting. But look at group 1. The response really drops. Why? Because A in group 1 was inhibitory. X in group 1 was excitatory. You add them together and it really reduces. Excitation, inhibition. Performance is a function of excitation and inhibition, taking both into account. So I'm just throwing some numbers out here. I'm just giving numbers to this. Maybe it helps you to visualize it, because I think the summation test, it's a pretty complicated thing. I think it takes some work to understand it. Maybe you picked it up right away. You're like, what do you mean? It's real easy. I think sometimes people are like, what are you talking about? Group 1, A and X in the summation test. X, what's its value? A, what's its value? So let's just give it some numbers. Excitation, let's say, is a scale from 0 to 1. And X has a really, 0 to 1, right? So X has a really high number, 0.8. It's a high value. X really signals reinforcement. Inhibition will give this a negative number, from 0 to -1. And stimulus A has inhibition, which I'm representing here as a negative number. 0.8 plus a negative 0.6 is 0.2. Let's look at group 2. X, 0.8. They got lots of training, really high. A doesn't have any meaning. It's 0. Never seen A before. This is the first time I've ever seen A, says group 2, if they can talk in their head. So 0.8 plus 0, still 0.8. So we can see if these numbers are representing responses, really low here, remaining high here. Now, differential conditioning, the reason we think it's going to be inhibitory, A is going to be inhibitory, is again this sort of idea of context, where they are. There's a lot of stimuli. And if the animal, let's say, is in an auto-shaping design, a little bird, and the blue light comes on and it gets reinforced, but when the yellow light comes on, it's not. There's still something there. There's the shape of the key light. Maybe it's a circle, maybe it's a square. The sounds, the cage, all these things are places where sometimes the animal does get some food. And so in a way, we get XB plus, X in this case will be the context, but not the context and A. So X is the context. I'm saying, the cage and the shape and the smells and the whatever. The animal's not getting reinforced when sometimes when it's in this cage it gets reinforced, but never when A is presented. So A gains inhibition, and we do see that in this case A does pass the retardation of acquisition test. It's slower to condition than a novel or neutral or meaningless stimulus. And it also passes the summation test. It will reduce the response to a known exciter. Finally, we get to latent inhibition, and this is the controversy. So this is just, you just present a light over and over to the animal. Never gets food. There's no context here where it gets food. It's just looking at the yellow light. Every once in a while, and not too often, the yellow light comes on, the animal doesn't get anything. It doesn't get like food other times. It's just yellow lights coming on and off in this animal's cage. And at first it might attend to it. Well, what's that? But after a while it doesn't. But what we see, and this is why it's kind of interesting, is that yellow light will take longer to condition than another stimulus. The yellow light passes the retardation of acquisition test. Another way of describing this, we call this latent inhibition. Latent means hidden. Sometimes it's called the pre-exposure effect, the CS pre-exposure effect. Show the yellow light a bunch of times and then try to condition it, the animal's a little slow to condition to it. We call that a pre-exposure effect. If it passes the retardation test, it's slow to condition compared to a brand new stimulus, but it fails the summation test. And if we want to say that something is truly inhibitory, we're going to have to say, oh, it has to pass both tests. So here's a little complicated experiment. We're starting to use a lot of these X's and B's and A's and just letters to create or represent stimuli, these variables. So I'm hopefully you're kind of getting used to them by now. Group 1, B plus, BA minus, back and forth. Train X all the way up. X is a really strong stimulus. So this might be a light, a tone, and a bell, whatever. And then we test the summation test. Then we just test it once, maybe a couple trials. Well, what's responding? And then we do many trials of acquisition to test how slow it is to condition. Now, what do you think would happen? What you've learned so far. A is a signal of non-reinforcement when in a context that it should get reinforced. So this is condition inhibition. A should be truly inhibitory. And it should reduce the response to a known exciter. The animal responded way up to X, and that's reduced when A is present. If this is auto-shaping, it pecks 95% of the time here, but 40% of the time here. And then we would also find that A takes a while to condition, to really signal reinforcement, to be excitatory. Why? Because it was inhibitory, and now you kind of have to change the animal's mind. Now we have another group, a control group. And we find C is inhibitory, but C isn't used here. A is neutral. A is meaningless to group 2. So A doesn't pass the summation test. It doesn't reduce the response to X because it doesn't mean anything. The animal's never seen it before. And it conditions just fine, really fast. It's a neutral stimulus. I'm ready to learn about it. Finally, this is stage 1, right? Group 3, this is the latent inhibition group. Just present stimulus A over and over again. Nothing. The animal doesn't get food, doesn't normally get shocked, doesn't anything. It's just the stimulus comes on now and then. Then we train up X, and we find that A doesn't really reduce the response to X, but it is slow to condition. So group 1 really reduces the response, in the summation test to X, because X signals reinforcement and A signals non-reinforcement. It's inhibitory, so it reduces the response, summation. But group 2 responds just as much to X, and group 3 responds just as much to X, even though A and X were together. And A had been seen before in this group, but it doesn't seem to affect the animal's response. That tells us that A is not inhibitory in this group because it doesn't reduce a conditioned response to a known exciter, which is X. But if we looked at how slow it conditions, group 2, let's go back, group 2 is being trained on A, but group 2 has never really seen A. I saw a little bit here, but that was only in a test. So A is neutral, can learn really quickly. But A is inhibitory here. Not sure what's going on there, but it's still slow to condition. That's group 3. Group 3 here in gray is the latent inhibitor. So the question is, why? Well, people kind of think they know why. The reason that it's slow condition has to do with habituation or a loss of attention. Can't learn to that which you don't attend, and A has been showing up in its cage for a while now, and I looked at it, and then I tended to it, and then I stopped caring about it, and then I stopped looking at it. And now you're telling me it's associated with food. I'm just not paying attention to it anymore. I've habituated to it, and so it's just going to take me longer to finally attend to it and then start showing those associations. Okay, so inhibition is a pretty complicated thing. It's a signal of non-reinforcement, and we have to have tests for it. So we do the retardation of acquisition test. A condition inhibitor, something with true inhibition, is slow to condition compared to a control. And a true inhibitor reduces the response to a known exciter when presented in compound, the summation test.